technically, quote unquote, make up your image, because if you have a lack of a photon that reaches the image receptor, well, that looks like white. If you have a photon that does reach your image receptor, whether it's transmitted or scattered.
I mean, the bony structures, I'm sorry, the bony structure, what beam makes up the bony structures? What do you call that beam? The attenuated beam, because you said only.
Well, it's the
lack.
it's the differential attenuation, I guess, is what you wanna look at there. So if you're looking, the reason why you can see bony structures is because you had a lot attenuated in the bone, but not very much in the soft tissue, which makes the bone, because of the high differential attenuation, it makes the bone stand out.
So it's just the loss of energy of the photon that interacted with the calcium on the bone.
It wouldn't be because of photoelectric.
Well, the photoelectric is going to be what makes the bone appear white, yes, if that's what you're asking. But again, your image, you know, if everything underwent photoelectric interaction, your image would just look completely white. And if everything went at Compton, transmitted your image receptor, it would look completely black. The fact that we have differential absorption, differential attenuation, where some tissues absorb more than others, that make us, you know, be able to determine what kind of tissue it is. So it's all three of those interactions that actually make up your image. All right, so let's go to photoelectric interactions and talk about what's happening there. So, I know we've talked about this before, but who wants to tell me exactly what's happening in a photoelectric interaction, as much as you can tell me? What's going on in a photoelectric interaction? Good.
The photon comes out and interacts with the nucleus. No. Oh, it's the outer shell, right? I don't know.
So an X-ray photon interacts with an inner shell electron, and then after that point, yes, then you have the cascading down, where the outer shells are going to come down, fill the voids. Now, something very important happens at that point.
They all get red photons.
Okay, produces a secondary characteristic X-ray photon, and it has very low energy because it's got very low atomic number, because we know everything in the human body is going to have a low atomic number. And it's simply absorbed, exactly. And there again is why it looks white on our film. If we have something in there that goes a lot of photoelectric interactions, it's going to look white, because the X-ray energy is just simply absorbed in that particular area. Okay, now, we also said that there are, which is going to be one of your essay questions, by the way, this is the next thing I'm about to talk about. Excuse me. There are 3 rules that generally govern whether a photoelectric interaction will take place or not. What was one of them?
This is a high atomic number.
Okay, it's got a higher atomic number, which means the electrons have a higher binding energy. It is more likely to happen. That is
Closer
very
the
true.
energies are to each other, likely interaction.
Okay, the closer the X-ray energy is what the binding energy of the electron, the more likely it is to occur as well. And there was one more. Okay, it's got to have more energy than the K shell, or not just the K shell. It's got to have more energy than the electron binding shell that it's interacting with in order for that to happen. We did say that rule is pretty much insignificant to us because our X-ray photons will always have enough energy for that interaction to occur. All right. What else did we miss on this? Let's go to the second interaction. That is very relevant to us, or it happens quite a bit. I'm going to take an X-ray Compton. You tell me exactly what's happening during a Compton interaction.
Photon comes in outside of the loosely bound outer shell electron, which is reinforced. It also produces a secondary scatter.
Okay, good. So X-ray photon ejects an outer shell electron. That becomes known as the recoil electron. In the process, that original X-ray photon scatters in a different direction. Okay. I guess simply put, are we more concerned with the recoil electron electron that was ejected or the scattered photon?
Scatter.
The scattered photon, exactly. Why are we more concerned with that?
Occupational dose.
Leads to occupational dose for one thing.
As a percentage.
Exactly, it has, most of the energy of that incoming X-ray photon is gonna be in that scattered photon, which means it can escape the body and hit us, which causes occupational dose. It can also fog our film, which is another bad thing. We don't really want our film to be fogged, but scatter radiation will do that. Not only can it lead to occupational dose, but let's just say theoretically, I'm taking an X-ray in here, I've got a scattered X-ray photon, I don't have lead in my walls, what can it possibly do out here?
Cause those people walking by or anybody out there.
Can cause dose to the general public. So that's why we first and foremost need our standard X-ray rooms to have lead-infused walls. And also, when we do mobile X-ray,
Make sure people stand at least 6 feet away, exact distance issue.
get the people that aren't involved with the X-rays as far away as possible. So that's why you want to have everybody leave the room. Remember, you're bringing an X-ray source into a room that's not designed to protect against X-rays. So you want to make sure you have everybody as far away as possible. Okay. So just to sum up there again, photoelectric interactions are the primary source of patient dose, while Compton interactions are the primary source of occupational dose. Well, with that said, hence the word primary that's thrown in there that the book tells you, because Compton scatter can in fact lead to patient dose, increase the patient dose. That is also true, because you could have a Compton scatter photon that's produced, scatters, and then undergoes another interaction in their body yet, which produces a photoelectric subsequent interaction, which would increase their dose. But primarily speaking, generally speaking, once again, what I want you to know, occupational dose is mainly caused by Compton, patient dose mainly caused by photoelectric. All right, so we have three other real quick interactions that we also talked about. Coherent scatter, what's that all about? Coherent scatter.
It's low energy.
Okay, it involves very low energy. You see it primarily below 10 keVs to be specific. What else?
And it's more than likely to be absorbed before it interacts.
Okay, so you don't have ionization with this because we don't have an electron that's ejected. It's simply absorbed by either the entire atom or by an electron. And after the initial energy is absorbed, what happens?
It raises the entire energy level of that atom and it generates a photon.
Okay, so that would be true. So essentially, for a very brief moment, that atom or the electron it's involved with would have a higher energy, but then that energy is going to be re-released in the form of a scattered X-ray photon. Is there any energy loss between the incoming X-ray photon and that scattered photon? No, because you didn't have ionization occur, so there's no energy that was lost because nothing was knocked out of its orbit. You're simply going to have a scattered X-ray photon that has the exact same energy, the exact same wavelength, and the exact same frequency as the incoming X-ray photon. Okay, two more just real quick, because I know it's break time just about. Let's start with pair production first. Pair production, what was that all about?
It interacts with the nucleus.
Okay, the X-ray energy is completely absorbed by the nucleus, and then what
Over 10
happens?
kV.
It creates positron and negative.
Okay, positron and negatron are released by the nucleus. Before we get any further, at least what energy is going to be required for this interaction to occur?
Above 10 kV.
It's about 1.02 megavolts, which would be about 1,000 kilovolts. Okay, those two particles that were released by the nucleus, one of those is going to act like a normal electron, one of them not so much.
Negatron actually, normal electron, and positron is volatile, I guess
Very
is the
good.
best word I can come up with.
All right, so the negatron's going to act like pretty much just a normal electron. It's going to find some outer shell void to fill in. No harm, no foul. The positron is the one that we're concerned about, because it's considered antimatter. It's going to combine with the closest negatively charged particle, which is normally graphene electron that it can combine with them and cause a little blast of energy to be created. It's gonna change matter into energy. And that's called what? That whole process? Annihilation reaction, or annihilation effect. Okay, let's go ahead and take a look. When you guys get back